moving into Cosmic Morning. Our first speaker is Andi Burkert, who's going to talk about cold, thin disks in the very early universe. So,
Okay, thank you, Colin. So actually, I would start with celebrating Colin. We just figured out he's been doing this now 10 years, not in a row because of, we just say 10 years. And so we should really have to celebrate because he does a wonderful job, you know. For me, this is the most important conference of the year. And usually when I go home, I have a whole year to work on all these ideas. And then I come next year and another year of new ideas. So thank you very much for doing this. So I would like to talk a little bit about paradigms, because I think paradigms are dangerous. You believe them, and then it takes a long time to figure out it's not worth anything. And there's a high redshift paradigm with actually three. One is that star-forming galaxies are gas-rich. The gas fraction, m gas divided by the sum of gas and stars, is of order 0.4. Then they are baryon-dominated. That means if you look at the dynamical mass, 2 V rod squared times half mass radius divided by g. It's basically given by gas and stars, and you don't need dark matter. And the third one is that you have a large random motion. That means V rod over sigma is of order 5 or something like that. And one can understand it in some easy ways by just looking at this tumor. Let me see whether this works. Yeah. This is now, meeting will be recorded. Okay, thank you. If you look at the tumor criterion, which determines under which conditions gas disks are forming stars, and there's this famous tumor Q parameter, which consists of stabilizing effects like random motion or pressure and shear, and the destabilizing effects, which is gravity. And the general wisdom is that this tumor Q regulates to something of order 0.7, and you can rewrite, let me see, Q in the following way. It's square root of 2 times the dynamical mass over the gas mass times sigma over V rod. And if this is 0.7, then you immediately see that sigma over V rod is of order 0.5 times m gas over m dynamical. And if galaxies are gas dominated, and if dark matter doesn't play a role, this is of order unity. And no wonder you get galaxies that have a large random motion and are kinematically hot. So this is the paradigm we have been living with for a long time. And now with James Webb, we begin to see other things at high redshift. And all our paradigms crumble, disappear, and we learn the universe is much more, let's say, innovative than we can think of with our little brain. And so basically one of them I would like to discuss is Revels 25, which is an ultra-cold disk at cosmic dawn. There have been ALMA observations of carbon-2 emission, which traces the cold neutral gas. And from these, it was worked out that this is a high redshift galaxy, it's redshift 7.3. Half-mass radius is typical 2.2 kiloparsecs. And rotation is quite large, 374 kilometers a second. This leads to a dynamical mass of 1.2 × 10^11 solar masses, but the stellar mass is only 8 × 10^9 solar masses. And so the authors said, okay, then the rest must be gas, because there's no dark matter of any importance in high redshift galaxies. And so they worked out the gas mass must then be 1.1 × 10^11 solar mass. And they said this is good because, you know, the star formation rate is 200 solar masses per year. Now, the gas fraction then is of order 0.9, and that would tell us that V rod over sigma has to be 2. And the surprising observation is that sigma is only 30 kilometers a second, so V rod over sigma is 11. And so the people were fascinated. Their paradigm broke down, and they said a big puzzle. Now, this is my version of the story. This is the rotation velocity which has been measured in this galaxy, V rod kilometer per second, where the distance r. These are the observations. You see error bars are quite big, so you can play with models if you want. And here I now put an exponential disk in with the right scale length. We know that the surface index is of order unity, so this is correct. And if you really want to explain this rotation by the disk alone, then indeed you need about 10 to 11 solar masses of this kind of galaxy. Now, there are a couple of problems with this idea, and one of them is that you don't know the gas mass, but you know the luminosity of carbon, C2, and it's 1.8 to the 9 solar luminosity. The gas mass we can work out if we subtract the stellar mass is 9.2 to the 10 solar masses, so the gas over luminosity fraction is 50. And this is simply too high. You know, if you look at the recent papers, M gas over carbon luminosity is less than 20. So there's simply, it doesn't really work. And the other problem is, indeed, if you use that much of a disk, then if you would have a tumor Q of 1, it would lie here along this line. So the velocity dispersion would be quite large. Here are the observations. And that requires really a very, very small Q parameter. In fact, if you believe that disks regulate to something of order unity, you would get a V rod over sigma of 4, which we all assume. But this galaxy has a V rod over sigma of 11. So that would require a Q of order 0.2. Now people say, why not? Why not 0.2? But 0.2 is impossible. And the reason is that when you have a disk that is highly tubular unstable, any little center of gravity, any enhancement in density will lead to local collapse. And you get something which is of that order. Everything collapses, and that leads to a non-random component in the non-circular component in the velocity. Now it is all collapse velocity, but as an observer you don't resolve these collapsing centers. So for you it's like a dispersion. And so you would interpret this as a Q going up, becoming very large. In fact, you can show that on a tumor time scale, this effective Q, which is not, it's not random motion, it's not pressure, it's collapse, but who cares? It's local collapse, would easily go to order unity. The time scale in which it would do this is a tumor time scale, which is 0.1, the orbital time scale times Q, divided by 1 square root of 1 minus Q square. And now you can say maybe the galaxy is so young that it couldn't yet get to these high velocity dispersions. Now, Rebus 25 is an orbital time scale of 407 years. If you put in a Q of 0.2, then the time scale on which this random motion would generate an effective Q of 1 would just be 8 in the 5 years. Now you might say, okay, this galaxy is younger than 8 into the 5 years. Well, why not? The universe is good for a surprise. But the star formation time scale is much longer. The star formation time scale is the mass of stars divided by the star formation rate. 8 to the 9 solar masses divided by 200 solar mass per year gives us 4 to the 7 years. So star formation has been going on for 52 more time scales. Plenty of time for these instabilities to raise this kind of effective random motion to a tumor Q of 1. So this is not the solution. And so what is then the solution? Well, you guessed it, of course. You cannot neglect dark matter, even at cosmic dawn. And so what I did is I just included a dark halo, and I didn't play around with it much. It took a standard NFW halo. The density distribution goes as 1 over r in the inner region. In the outer parts, it goes as 1 over r to the third power. We know the redshift. And then if we fix a real mass, then we can work out the density profile. The real mass then is given by the critical density times RV to the third power. The critical density we know from the redshift, from the Hubble constant. We can put it into here. Then we work out RV. Then if we have M and RV, we can work out rho 0. So we have the full information about the density distribution. The only thing we need to fix is the scale radius. And the scale radius is usually a function of the real radius. It's the real radius divided by some concentration. And I went to Volker Sprigl and said, tell me the concentration of dark matter halos at redshift 7 to 10. And he said, Andy, I never looked into this. And it's funny, concentrations have been studied, but at high redshift, because people never believed that dark matter plays any role, nobody has looked at the concentration of dark halos. So I said, you did? What did you get? Oh, 4? Yeah, no, so 4. That's, yeah, good. Ta-da! So I put 4 in because I didn't. Yeah. So I think it's probably like 4. So I put 4 in, and then I have the density distribution of dark matter. So now I have only 2 free parameters, which is the viral mass and the disk mass. And of course, you can play with them and fit the rotation curve, and it's a little degenerate. So I have to fix it somehow. So I said, okay, I take the carbon luminosity, LC2, it's 2^9 solar luminosities, and believe this kind of estimate of how you convert carbon luminosity to gas mass. Then you get a gas mass of order 3.6 × 10 solar mass. You add the stellar mass of 8^9, so you get a disk of order 4 × 10 solar mass. Why not? So I put this in, and then I get this kind of result. So these are the observations again. This is now my disk contribution to the rotation curve. And then I have to fix the viral mass of the halo such that I lie along this line. I have no freedom. And you see I need a viral mass of 2.2 × 10^12 solar masses. And you see this is the contribution of the halo. And what you find is that the halo is actually more important than the whole gas, the whole baryonic disk. In fact, if you then look at the Tumri Q, here this kind of bar shows the observations. Then between a Q of 0.7 and 1, you lie perfectly along this kind of observations. So it fits very nicely, and you do not need a small Q value. So at first, I was very happy with this result. But then, of course, you talk to people, and people say, Andy, garbage. Because the baryon fraction is 2%. These are high redshift galaxies. Now I said, how do you really know that it need to be larger? They don't know, but okay, I said, okay, let's believe this is more or less garbage. What can you do? You can, of course, put more dark matter in the inner region by making the concentration higher. 8 would do it. And then I can lower my viral mass because I have more fraction of the dark matter in this inner region. But as Rachel says, concentration is 4. Okay? Oh, no, this is, no, you're my reference for that. So I thought of something else.
What's the bar problem? What is the bar problem that you're worried about?
The baryon fraction. The bar problem. The baryon fraction. If you just, take the disk mass, the baryons in the disk divided by the viral mass, it would only lead to 2%. Yeah, okay, good. Okay, so then actually we are now here celebrating Blumenthal and Faber and Premack. And I went to an old paper, of 1986. And they talked about dark matter contraction, adiabatic contraction. And they said they must be everywhere. If you have baryons in the inner region, they deepen the potential. Well, dark matter has to contract. Now there's another paradigm, we never ever see it. And I think it's not a paradigm, it's a puzzle. At low redshift. But maybe at high redshift there is more evidence for dark matter contraction. Actually in numerical simulations you always get contraction, but when you look at observations, you rarely see it. And actually we did a recent paper in 2002 on that, where we looked at the adiabatic contraction, and indeed if you start with this in the Hornquist profile, you add a disk, it doesn't really matter, you can add a spheroid, then you can show by numerical simulations that you get a result which is very close to the predictions from adiabatic contraction through this kind of line. So it works. So I said, okay, maybe this helps. And now you see the result if I take this adiabatic contraction into account, just taking my disk as I have it. And the halo is still dominating, the disk is still smaller, Q is perfect in agreement with observations, the rotation curves can be fitted, and now I get a viral mass which is smaller, and a baryon fraction which is in good agreement with the rest, with what I would expect. So maybe this is a first indication that very high redshift galaxies show contracted halos. And if it is true that at low redshift we rarely see it or seldomly see it, it means that afterwards some process happened that remove this contracted component. Could be feedback, could be whatever, annihilation, you see? So it could be anything. So maybe you find more contracted dark halos at high redshift if you do this kind of analysis, and then something happens between cosmic dawn and nowadays. Now the question is, of course, why does this galaxy have such a dominant halo component? And I think the answer is angular momentum. And yesterday we said we don't talk about angular momentum, but it's crucial. It's very important. Well, it's usually given by the lambda parameter, which is the specific angular momentum of the disk, divided by RV times VV. And this is the angular momentum lambda distribution, which you expect from dark halos. And if you believe the disks have something similar than that, then here would be most of the disks, and then you have a tail with high angular momentum and a tail with low angular momentum. And here's now my Rebels 25 solution. I just take the dark halo and the disk as given, and all I change is disk scaling, so angular momentum. And then I see how the scalings depend on lambda, or the lambda depends on the scalings, and you see the small lambda indeed would predict that this type of galaxy would be very compact. But you see, when you go to large lambda values, the disks really flare very quickly. And here's my Rebus 25. It has this kind of R1/2. So I see it has a specific angular momentum which is quite large, much larger than the average, a factor of 3. And no wonder that it is dark matter dominated, because it extends much farther into the dark halo. And indeed, here you see the V-rot over sigma as function of the assumed lambda of my disk, or the scalings. And you see, indeed, if you would have disks left of this kind of peak, they have a V-rod over sigma which is small, we expect. But when you go to the extended disk, V-rod over sigma flares very quickly. And so if you have these large disks, you would expect, indeed, from very simple physics, that they should be completely rotation dominated. So nothing is wrong about Rebus 25. Nothing is surprising. It's just standard physics, which we know in the present universe. And the only important part is you shouldn't forget about dark matter, also at cosmic dawn. That's all I have to say. Thank you very much.
Questions?
I ran out of time yesterday, but I was trying to draw a parallel between TNG models and low redshift galaxies, specifically their behavior in radius versus mass, star-forming galaxies. And the TNG models clearly show signature of adiabatic contraction, and they match the data pretty well. So I'm concluding that actually low redshift star-forming galaxies, if we model them, will show the very phenomenon that you're talking about.
Very interesting. I haven't found evidence, so that's interesting. Well, the TNG shows it, but the observations show it too.
With the same characteristics.
Ah, good. Okay, I thought it's only in the simulations.
Hey, Andy. So,
where? I hear.
Way in the back. Sorry. So I think that your conclusion that modeling the galaxy without dark matter leads to unphysical things is good, and that it's entirely plausible to construct a model in which the dark matter contributes significantly to the rotation curve. I just don't think that it's possible to measure the virial mass of a dark matter halo this way, because the rotation curve doesn't go out far enough. It's the same problem that we have at low redshift. Yeah. There are too many things that influence what goes on in the center. You can have adiabatic contraction. You can have mass outflow that then causes the core radius of the halo to expand and so on. So there's just too much galaxy formation to measure a virial mass with something that does not go out to the halo scale, an observational probe that does not go out to the scale radius. So what the virial mass of this dark matter halo is unresolved. I'm sure it is dynamically important, though.
Well, I would say in general maybe you're right. But in this kind of case of very extended disk where halo dominates everywhere, maybe it's easier. It's like dwarf galaxies where we can get more information about the dark halo, even if because they are so much dark matter dominated that even the inner regions tell us a lot. Of course, I have to put in the NFW profile, And if I put it in, and if I'm completely dark matter dominated, then in the inner regions also tell me what the real mass would be, isn't it?
You're inside a couple of kiloparsecs, and there's processes in the formation that can modify
Oh yeah,
the
I
halo
agree.
profile.
I agree,
So it's
of
not
course. I
strictly
agree with you.
NFW anymore.
Yeah, you're right. If it's not NFW, if it is a chord, or what do I really know, then of course I'm lost. I agree with this. Yeah.
All right, I think we're going to have to move on, but there will be discussion at the end of this session. That'll be more time to discuss this. So let's thank Andy one more time.
Thank you.